This is your lesson for solving systems of equation using inverses of matrices and determinants. It follows the notes set by Glencoe 4.6 and 4.8. The first example we're going to take a look at involves a 2x2 system of equations. We're asked to solve it using Cramer's rule. Cramer's rule states that we can solve for variables using determinants. X will be equal to the determinant dx, and we're going to divide him by determinant d. Whereas y will be solved by creating determinant dy and dividing that again by determinant d. The first determinant that we're going to find is determinant d. He is created by simply making a determinant using the coefficients for each variable. Each variable gets their own columns. The first column we're going to use is for the coefficients of x. The second column we're going to use the coefficients for y. Just like we've been doing, we have our downward diagonals subtract our upward diagonals. So downward diagonal, 5 times negative 5 gets me negative 25. Upward diagonal, 2 times 7 gets me 14. We always subtract down minus up. So negative 25 minus 14, that gets me negative 39. This will fill in the denominator for both my x and my y. Now, how do we create determinant dx and determinant dy? Well, determinant dx is going to use the determinant d, but we are going to replace the x coefficient column with our solutions. Okay? So the coefficients for x are no longer a part of our determinant. However, the coefficients for y are still a part of our determinant. The solutions are going to fill in the first column because it represents the coefficients for x. Now, once again, downward diagonal, 13 times negative 5. 13 times negative 5. Well, if you can't do this in your head, let's do a quick trick. 10 times negative 5 gets me negative 50. 3 times negative 5 gets me negative 15. Negative 15 and negative 50, that gets me negative 65. Hope that helped. 13 times 7. Well, 10 times 7 is 70, and 3 times 7 is 21. 70 plus 21 gets me 91. Now we're going to subtract these. Negative 65 minus 91, that gets me negative 156. To calculate for x, we're going to take this determinant dx, negative 156, and we're going to divide by negative 39. Negative 156 divided by negative 39 equals 4. Now we're going to solve for determinant dy. For x, we replace the x coefficient column. For y, we're going to replace the y coefficient column with our solutions. So the coefficients for x are now again a part of our determinant, and our solutions, 13 and 13, will fill in the y coefficient column. Rinse, repeat, down minus up. 5 times 13. Well, 5 times 13, that's 5 times 10 and 5 times 3. That's going to get me 65. Then we're going to do upward diagonal. 2 times 13, that gets me 26. Down minus up, so 65 minus 26, that gets me 39. So to solve for y equals 39 divided by negative 39, which is simply equal to negative 1. Let's put our solution in our ordered pair for negative 1. And here's our solution to the system using Cramer's rule. Continuing right along, we're going to continue to use Cramer's rule, but now we're given a real-world system of equations using the votes from George Bush and Al Gore in the 2000 presidential election. We're asked to write a system of equations, and we are told to solve the system of equations. Something that you need in order to solve a system is variables. We are going to define the variables x and y as the total number of votes, because that's actually what we're trying to figure out, the total number of votes in each state. Because it's in each state, that also helps us figure out, well, we can let x be California, the number of votes in California, and y, we'll let that be the number of votes in Texas. Okay? Now, there's two key pieces of information given. We're given votes in California, and we're also given votes, the voting for George Bush and the votes for Mr. Gore. So, we're also given percentages for each of the states. So we're going to create an equation for the Bush and an equation for the Gore. Okay? So Bush, he received a total, he's the blue bars, 42% in California and 59% in Texas. So 42%, that's actually the same as my decimal of 0.42. And it's multiplied by the number of votes in California. And his votes in Texas were 59%, so 0.59y. That's going to be equal to our big number of 8,400,000. 1, 2, 1, 2, 3. Hopefully you can read that chicken scratch. Gore. Gore will be set up about the same way. So Gore, he has different percentages. That's the only thing we need to worry about, as well as a different total. In California, he received 53% of the votes, so 53% is 0.53. In Texas, he only received 38%, so 0.838. And then his total was 8,300,000. Okay, so here's our system of equations. Now we're going to use Cramer's rule to solve our system of equations. Okay, so first off, we're going to find a value for x, and then we're going to find a value for y. Just to help me remember to use Cramer's rule, we're going to use determinant dx and divide it by determinant d. Okay, so determinant d, that's going to be using our coefficients. We're going to have a column for x and a column for y. So determinant d, our coefficients for x are 0.42 as well as 0.53. Our coefficients for y are 0.59 and 0.38. Okay, so this is one of those ones where I'm actually going to have you figure that out. Make sure you check your work. Okay, dx, we're going to set him up and we're going to replace the x column with our solutions. Big number here, and 0.59 goes fill in, and the 0.38 gets filled in. Check your work. This is also probably a good time for you to check out the calculator, and maybe you should Google where you can type in determinants and matrices using your TI-83. All right, so for dy, we're going to replace the column of y coefficients with our big numbers, and our x coefficients are going to go over back. Okay? So once again, I want you to try these determinants on your own, and then check your answers with your textbook. All right, this is our last example of Cramer's rule, and just like the previous one, I'm going to get you started on this, and then I'm going to have you finish it up. A lot of these examples are just going to end up being follow the algebra, watch for small mistakes, watch your signs, and watch when you multiply by 0. From experience, that's typically our sticking point. All right, so using Cramer's rule to solve a 3x3 system of equations, we're still going to follow the normal protocol. X is going to be the determinant dx, and we're going to divide that by determinant d. The only difference now is the fact that determinant d is going to have coefficients for 3 variables. So, oopsies. It's going to have 3 columns, and it's 3 equations, so it's going to be a 3x3 determinant, okay? So determinant d, let's worry about him first. First column, I'm going to fill in my coefficients for the x values. Then my second column, I'm going to fill in the coefficients for the y values. It's important to recognize coefficients that are 1 still exist, so there's still a coefficient of 1. And there we have determinant d. Okay, I'm going to skip the process of figuring out all the math in front of you, but we go to figure out that the determinant d is going to be -9. Okay, if you want, pause and make sure you can do that algebraically on your own or use the calculator. Now determinant dx. We are going to replace the x column with the solutions of our system. So -1, -9, and 5. And the other ones will remain the same, okay? The only times a column will change is if we're looking for that specific variable here. So dx, if you do the math, you'll get -2. Once again, maybe you want to pause here and figure out, can you get the right answer? So that tells me that x value will be dx over d, so -2, divided by -9, a negative divided by a negative is a +2/9. Fractions happen in life. I promise you it's going to be okay. All right, let's do dy, and maybe you guys can do dz on your own. So dy. We are not going to replace the x column. He's going to be back to the normal x coefficients. We're now going to replace the y column. Maybe that'll help the squigglies. And I'm going to replace it again with our solutions, -1, -9, and 5. And little z, he's just still staying the same. dy, when you go to calculate him, you find that the determinant is equal to 12. So to solve for y is equal to dy divided by d. Determinant dy was 12, and determinant d was negative 9. 12 divided by negative 9, y is now equal to negative 4/3. Okay? Try dz on your own. Try doing these determinants on your own, as well as try to find how to plug them into your calculator. That'll be a great way to check your process. All right, we're about to finish up 4-8, last section. So the first thing we're going to try to do is create a matrix system of equations of a two-variable system. So we have our system here, and the first thing we're going to create is a coefficient matrix, where each of the variables gets its own column. Once again, that's pretty much the same as Kramer's rule. But now we're not dealing with determinants, we're back to matrices where we have brackets. We're now going to create a variable matrix, okay? Just to quickly show you why this works. When we multiply matrices, because that's actually what's happening between these two matrices, we're multiplying them. We do row times column, okay? So that would be 5 times the x plus the negative 6 times the y, and ta-da, didn't that create our first equation? Just wanted to quickly show you why that works. And then we're going to set it equal to our solution set. Okay, so now the solution set is going to get its own matrix. And just so you know, remember, corresponding elements can be set equal to each other. So that's why that works. It's kind of exciting. All right, so now we're going to get into some real world problems where we, again, must first create the system of equations. All right, it's almost like we're in Miss Bilkey's class right now. Here we are dealing with some glucose and some sucrose and creating a system of equation that represents the weight of each atom. And that kind of helps us out because it tells us we need to create two equations, one for each is it a compound or a chemical? Molecule. Don't tell Miss Bilkey. All right, so we need to create an equation for glucose and an equation for sucrose, and the total weight, which is nice because it's telling us what it's going to be equal to, is given in our chart. And when we're adding up all these different compounds, that's why we're going to add up to this total weight here, okay? And it's also nice because it kind of tells you how many of each compound. And so what we really initially are seeing here for glucose, we're going to have 6 carbons, we're going to have 12 hydrogen, we're going to have 6 oxygen, okay? And the total will be set equal to 180. Now the thing that I just picked up while reading this lovely problem is the fact that it gives me the mass for one oxygen element. So I can actually plug in the weight of oxygen as 16, okay? That's why the glucose is actually, if I simplify it, so 6C plus 12H plus, 6 times 16, that's going to be 96, okay? I also have it set equal to something. We just can't see that. So let me zoom out here. A little too far. We'll put it over here. This is going to be set equal to 180. Okay, I'm going to bring my constant onto the other side here by subtracting 96 from both sides, giving me my lovely glucose equation of 6C, so 6 carbon, plus 12 hydrogen, equals, 180 minus 96, it equals 84. We're now going to repeat the process for sucrose, but it's going to be a little bit different. So 12 carbon plus 22 hydrogen plus 11 oxygen, but we already figured out we've been given the oxygen value of 16, so we can plug that in, equals 342. So 12 carbon plus 22 hydrogen, 11 times 16, that gets me 176. Just like before, I'm going to subtract both sides by 176. And then that'll give me my 12 carbon plus my 22 hydrogen. It's going to be equal to 166. This is my system of equations. So now, last thing, got to create a matrix equation. Okay? So here we go. Once again, we have our coefficient matrix. First column will be for carbon. Second column will be for hydrogen. And we're going to multiply it by, let's just use C and H. Why not? We can keep up with it. And it's going to be, say, equal to our solutions, or in this situation, our total mass or our total weight for each atom. All right, matrix equations actually solve the system. So first off, we need to set up our matrix equations. We have our coefficient matrix here with our x column and our y column. We're going to have our variable matrix, x and y. It's going to be set equal to our solution matrix, okay? The goal in solving an equation is always to isolate your variable. Now we have these coefficients, and our gut always tells us to divide them away. Well, guess what? You didn't learn matrix division. It doesn't happen. What does happen is we can multiply both sides by the inverse. Because the beautiful thing that happens when we multiply both sides by the inverse is it's going to make our coefficients become 1, okay? So I'm going to denote that by my raised to the negative first power here, showing all my steps. And we must balance our equation. What we do to one side, we must also do to the other side here. So I'm also going to multiply the inverse onto the right-hand side, create my balancing act. All right, so inverse times itself, well, not itself, times its original matrix creates our identity matrix. Here's our lovely identity matrix. He creates the lovely identity properties that are just going to leave my x and my y all by itself, okay? What I need to focus on here is the right-hand side of my equations. So the inverse, first off, I need to find the determinant of this matrix here because I'm going to divide everything by the determinant. So you got to do your downward minus your upward. And if you do that, you're going to get negative 54. Now, would you really want to have had that in there before you started multiplying? I don't think so. We also got to do a switcheroo of our downward diagonal and changing the sign of our upward diagonal. And now we're first going to decide to do some matrix multiplication and then we'll deal with the scalar, okay? So 1 over negative 54, we'll do that in a second. So here we go. Negative 8 times 11 plus negative 2 times 1, that gets me negative 90. Now we're going to do row 2 times column 1, row 2, column 1, negative 3 times 11 plus 6 times 1. That gets me negative 27. Hopefully you're remembering your scalars. So now we're going to distribute in our 1 over negative 54, aka just divide everything by negative 54 here. So our values for x and y are going to equal, well, negative 90 divided by negative 54. That'll simplify to being 5/3. Negative 27 divided by negative 54, that simplifies to being 1/2. And now we have our values for x and for y, okay? So now we're going to continue on and go down to example 4. Now, using systems of equations to solve problems with no solutions is going to be really, really quick, okay? The giveaway. A system's not going to have a solution if the determinant of the coefficient is 0. Okay, because obviously you can't have an inverse if your determinant's equal to 0. So quickly on this one, I'll just prove that fact. Here is going to be our lovely coefficient matrix here. Okay, we'll just set up the equation just to be politically, well, not really politically correct, just to be correct. Okay, so I'm going to cheat it. 6 times negative 12, that's going to be negative 60 plus negative 12, so negative 72. Minus 8 times negative 9, that's going to be also negative 72. Negative 72 minus negative 72 is 0. The determinant equals 0, which means no inverse. And if there can't be an inverse, we can't solve the system. So ta-da, there's no solution. Hopefully remember that when there's no solution, you learned way back when that this means that our system is called inconsistent.